Okay, let's make a start. So today I'm going to be talking about parsing, particularly for context-free grammars, which is a particular type of grammar. David told you earlier this week about the different levels of grammar, the Chomsky hierarchy, and so you have some knowledge of what the distinctions are between those. And so what we're going to be talking about is one particular algorithm for one particular style of grammar. The grammar might be automatically learned, it might be handwritten, it might be discovered from somewhere. Presumably that still means it's learned or written. I don't think they spontaneously appear. Given a grammar, how can we actually parse it? And I'm going to go into for one particular algorithm for doing this. Just as a reminder of where we are in the course, what we've really been doing is we're talking about different levels of language processing. We talked about some low-level things like orthography, tokenization, talked about morphology, we're talking about words, and we've been talking about syntax, basically the structure of language, because it's important, okay? Sometimes it doesn't matter, but sometimes it's ridiculously important to actually understand what's going on. Human communication seems to like having structure in the language, no matter what language it actually is. All languages have grammar, and being able to represent that means that you can actually do the things that you want to do, ask questions, answer questions, give summarization, identify who's doing what to whom, and without it you will sometimes make errors. Sometimes. Okay. Now sometimes that bag of words things are just fine, and the order of the words is not important, but usually that's for pretty shallow processing, and the harder you're trying to get the information out of the natural language, typically the more important syntax actually is. Now again, I want to remind you, we're not here as a prescriptive view about this is what grammar is. There is no one definition of what English or any other language's grammar actually is, in spite of what your elementary school teacher told you, where there's a correct way and a wrong way. The answer is what people do is grammar, okay? And we're not saying that that certain things are wrong. We're not saying that in Pittsburgh, the local dialect here, you can say something needs cleaned or needs fixed, which apparently is not in standard American English. It needs to be cleaned or needs to be fixed. But locally you can say needs cleans and needs fixed. I'd like to point out in my dialect, Southern Scottish, that's fine too, okay? And so when I came here and people said they've got these really weird grammatical forms in Pittsburgh, and they gave the example to me, I said, what's wrong with that? Because it's just fine for me. In fact, it probably is, because it's a whole bunch of Scottish miners came here 250 years ago, so there's a relationship there. But syntax is important, okay? Sometimes, okay? It definitely exists, and people who go, but we don't need it. The answer is you're not trying hard enough on the tasks that you're actually doing, because you do need it at times, okay? So we're actually going to talk about recognition. So recognition is the task where I have a grammar in a sentence and I want to know whether this sentence matches that grammar. Okay? I don't want to know what the parse of it is, I just want to know whether it's in that language described by that grammar or not. Well, parsing is show me how it's in that grammar, show me the rules that are actually there. And there are two different tasks. Okay, one is computationally easier to do. It's much easier to say whether it's in the grammar or not. It's harder to show me the parse, and we'll talk about that. I'm going to talk about two standard ways of doing the parsing algorithm, so-called top-down, bottom-up. We're going to give examples of that. I'm going to talk about Chomsky normal form, which is a standardization for context-free grammars, or at least some class of algorithms require your grammar to be in that form. And then I'm going to actually talk about the CKY algorithm. The CKY algorithm, I will remind you multiple times, stands for Koch, Younger, and Cassimi. And you're going to say, wait, you just said the CKY algorithm. And then if you take the initials of these people, it doesn't say CKY, it says CYK. And that's deliberate, and it just seems to be in random order. And some people call it the CKY algorithm, some people call it the CYK algorithm. And if you go and look at the papers, also isn't clear what it is. So both of them are the same thing, okay? And I just want to, they didn't actually develop it together. I'd always thought they developed it together until I looked it up. And actually, no, they sort of independently came up with the algorithm, and then it was put together, and all the names were put together. Two of them did it together and one did it separately, but I can't remember which way around it is. We do want to highlight this thing about parsing is sometimes critically important, and sometimes it isn't, okay? Just because you can solve a bunch of problems without syntax doesn't mean that syntax doesn't exist, okay? It just means that maybe syntax isn't needed for your particular problem that you're actually working on. Also, dealing with syntax is substantially harder, so it's a cost. So it's computationally more expensive. There's no guarantee that you'll have a grammar that's appropriate and will give you the right answers. So if you want syntax, you can try to get it, and it may or may not help, but you should be aware that it's a choice. So the example that, believe it or not, I didn't come up with this example, but it's really quite a good example. The student who was taught by Alan Black won the prize, okay? Which I must admit is a really nice sentence, because I'd like students to win prizes, okay? So who won the prize? And if you were just doing string matching, what you would discover is that in this sentence here, it says that Alan Black won the prize, okay? And of course, I know from the priors that we have that Alan Black never wins the prize. So I know that I didn't actually win the prize, but it has a sentence, the substring in there that says that Alan Black won the prize. But that's not what the sentence means. So who won the prize? The student won the prize, okay? And the student who was taught by Alan Black won the prize. And why is that the case? Well, the answer is syntax. And basically, there is a relative clause there who's identifying what student it was. Okay, it's not clear if it's a particular student or it's just any student who was taught by Alan Black. You should note that point, particularly won a prize, because that would be good for all of you. But there's a relative clause, and so really the core sentence, the subject is the student, okay, and that's the subject of one, and so who won the prize? The answer is not the immediate noun phrase, but the subject of the sentence. So you need to be able to parse it in order to be able to get that information. And that's, okay, a little contrived, okay, maybe, okay, especially with my name in it, but it's what syntax is all about. And you, as understanders of English, can tell immediately when somebody says the student who was taught by Alan Black won the prize, can answer the question who won the prize as the student, not Alan Black. Okay? But if you were just going to say, I'm going to search for the string won the prize, and I'm going to look for the noun phrase that appears immediately before, you'd get the wrong answer. Okay? And so this is a good example of why we need to care about syntax. Not everything has to care about syntax, because in some sentences the noun phrase that's immediately before won the prize would be the right answer. Okay? But it would also be the case that if you parsed that sentence and found the subject, you would be able to get the right answer too. So it's a trade-off. Okay? But be aware that there are these things where it's not the case that just looking for the localized thing gives you the right answer. Now, in order to be able to do this right, it will have to parse properly, and parsing often gives you the wrong answer or gives you another answer if you ask the linguist who built the grammar and the person who built the parser. They will show, or at least argue, but they will show, if you listen to them long enough, that the parse that they got is still a valid parse, but it might not be the right parse, okay, because you can get lots more parses in there. But if you did that and you can get the right, you can get the right answer out of it. You should always be aware of that, okay. We're going to talk about context-free grammars. We talked about these before. Context-free grammars have a vocabulary of terminal symbols. They're often words, but they might be part of speech tags. A set of non-terminals, okay, they're sort of variables. They're the things that are going to be expanded. We'll call them n. There'll be a special start symbol. It's often the letter S, but it could be some arbitrary token. And a bunch of production rules that go from the form of x to alpha, where x is one of the non-terminals. So basically, the non-terminals can be expanded as things. And alpha is going to be a string of 0 or more of non-terminals or alphabet symbols. Okay, standard rule, you're going to have x going to something, 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 something. That can be a mixture of non-terminals which can get further expanded, or terminal symbols that don't get further expanded. It can be empty, okay, and it can be arbitrary length, but it has to be finite length. Okay, otherwise you get weird cases. But there's nothing particular special or constrained about this. As David talked about before, human languages are pretty close to context-free. There's a number of interesting linguistic things that happen in language that can't really be dealt with by context-free grammars. Particular if you have lists of 1, 2, 3 ABC and they have to be the same length. You can't actually do that in a context-free grammar. However, in natural language, it's incredibly rare to find these. In English, the only example is use of the word respectively, where you have Bob, John, and Mary were a nurse, a doctor, and a policeman, respectively. But that's a really weird, specific case, and I don't think that list can be arbitrarily long. It would be weird if you were going to name 55 people and 55 jobs and then put the word respectively at the end. I strongly suspect the person listening to you will have already left by the time you've got to the fifth person. So we don't know if these sentences exist. There's a couple of weird things in Dutch and in Swiss German. David probably mentioned that his wife is Swiss German, so his home language is Swiss German, but he's not a Swiss German speaker. And every time he asks his wife about these unusual constructs in Swiss German, she says, "What? Nobody says that." But anyway, we're not allowed to know that. And Dutch has this thing about feeding the hippo. At least that's the standard sentence that is. They're marginal. For computational purposes, for most things, natural language is context-free, and it's only sometimes context-free. It might be able to get away with a really big finite state machine, but it's context-free is certainly good enough. And if you built a machine that could only do context-free grammars, but understand everything in natural language up to context-free grammar, people wouldn't complain. Well, they would complain because they'd say that the robots were taking over, but they wouldn't complain about the limitation of that natural language form. Because humans are a little limited in this way that you can't do really complex sentences. By really complex sentences, I mean you can't do the 55 people, 55 jobs, respectively. You can't have sentences that are longer than 100,000 words because nobody's going to listen to you. And so there are actually limitations in language from a practical point of view. So we are going to pretend that all of natural language is context-free. It's not, but we're going to pretend that because compared to all the other problems we have in natural language processing, this is an easy simplification and really not a problem. Okay, so everything is context-free, almost-ish. We're going to talk about two problems here, both recognition and parsing. So we're going to get a string of a sentence, okay? Bunch of words, all nice, white space separated, no punctuation. We're going to deal with easy things to begin with. And we're going to have some context-free grammar, G, that we're given, and what we'd like to be able to know is this sentence in this grammar, okay? Technically, it's not in the grammar, it's the language that's described by the grammar, okay, because the grammar is sort of a model. And we're talking about the language that G describes, and so we want to know if the list of words, W, is valid for the grammar. So is it grammatical, okay? And the other thing that we like to know is we like to know the parsing. It's a different problem, although sometimes it's solved by the same algorithm. What we like to know is we like to know one or more derivations. That's a technical term, okay, and we'll talk about what that is for W under G. So what we want to know is how would you get that sentence given the grammar? And there what we're wanting to say is we don't just want a number, a value yes or no. What we want to know is what is the bracketing within that, or what are the rules that you actually used in order to be able to show that it was grammatical? Because that's important. As I showed in the earlier example, I want the bracketing, okay, because I don't just want to know, yes, this sentence is grammatical, because I would like to know what is actually the noun that's related to won the prize and what bit's been bracketed away as a relative clause that I can actually skip over, okay. So these are two things, recognition and parsing. We can actually look at parsing as a sort of search problem, okay, and we can abstract away from it. And what we can do is we can actually say, well, we have a sentence that we start off with an S. I can keep expanding things from that until I get the sentence I want, okay? And that's what's called top-down. We do this in other things. We search for things given the thing we want. We try to expand what that thing is until we find what we're actually looking for. We can also do things bottom-up. So what we do is we look at the words, okay, so we're at the bottom, and what we do is we look at the words and see which ones rules can be used to join together, and we can gradually build up and see if we can find an S. There are two ways to do it. Okay, there are advantages and disadvantages to either. There are things that you will find one way that will be spurious that you won't find the other way, and some of them will have more work than others. Whether you end up with more spurious searches going top down or bottom up will sort of depend on how the grammar's written, but maybe sort of depend on the algorithm too. There are some people who claim you should only do one way and the other way is stupid, and I can't remember which way they argued, because it's both ways. You can find somebody who's going to argue that, and they usually have a good argument, okay, but the other people have a good argument too, and it sort of depends on it, but there are definitely both ways that you could actually consider doing this. Remember, parsing of language with respect to a grammar is fundamentally what we do in computer science when we're dealing with programming languages as well, okay? And so it's the same problem. It's exactly the same problem. And in programming languages, the grammar is pretty fixed, although, as we know, there's funny ambiguities that we get in programming languages with dangling else's and things like that, and so there has to be some definition of it. Though most programming languages are actually specifically designed, the grammar of them is designed to make it easy to parse and not have lots of ambiguity, because we don't want to make errors when we're actually writing programs, because we can't see the syntax properly. I mean, who would actually make, I've complained about this before, who would actually make white space tokens be significant in a programming language? I'm pretty sure that would never happen in any modern Guido, I'm referring to you, okay, if you know who he is. He's the inventor of Python. Tabs are weird, but anyway, let's not go there. Python's a great language, actually, if it wasn't for the tabs. It is the same problem, and maybe you've even done with these things, and it's an exercise that often gets done in computer science classes about parsing languages, computer languages, okay? And the algorithms are sort of similar, and they overlap in some way, but the amount of ambiguity that's in natural language is substantially more, and therefore you sort of maybe have to emphasize different parts of the algorithms when you're actually dealing with them, okay? In general, if you abstract away what the problem actually is, you can implement parsing with this very simple search thing. You can do an agenda-based form, and basically what you do is you start off with some initial state, and what you do is, while there is still something on the agenda, you're going to do it. You're going to take the top one off the agenda, or maybe you optimize to take the best one or the most likely one, but you take one off the agenda, you process it in some way which may generate more things to the agenda or not, okay? and then you check to see whether you've completed it or not. It's actually quite important to do that, otherwise you disappear in the loop forever. So if you're not at the final state, you can continue going because you might want to find all possible things, or you just want to find the first one. That's a choice, okay? And you keep doing this looping of processing, stuffing things on the agenda until there's none left, okay? Lots of algorithms do this. This is very, very, tree search is going to do something like this, and you're going to loop like this. And I'm going to show some basic algorithms that are fundamentally following this. Okay. Here's a very simple grammar for English. It's from the book. It really shows its age. Prize if anybody's old enough to remember what that airline actually is. See? Northwest Airlines. They were bought by Delta in 1837 or something. I don't think it was as old as that. I do remember flying with them. But they don't exist and haven't existed for a long time, maybe 20 years. But anyway, here is a grammar, okay, and here is, so it's expanding. It's relatively simple. It's all about flying, okay, and what I'd like you to do is, can somebody give me a sentence that is acceptable to this grammar? Yeah. Book on its own. That's a minimum answer. So we're going to go S to VP to verb and verb to book. Okay, so you're absolutely right. Okay, it's the command book. Okay, so it's be unusual to use it, but we're talking about flights, and so what you're saying is book. So yes, completely valid. Can somebody give me a different sentence? Yep. Me book. Okay, so we're going to do NPVP, and NP is going to be expanded to any one of these. We can do a pronoun, and pronoun can be expanded to me, and a VP can be a VP to a verb and get book. So me book. Okay. Okay, I'm going to change my question this time. You're absolutely right. Okay, but that was going to be my second exam. Can somebody give a nice English sentence which can be parsed by this set of grammar rules? Yeah.
I include a Houston.
I include a Houston. Okay. You have interesting English. So NP to VP. So NP can go to pronoun. Pronoun can go to I. Oh, verb is include. Okay, so VP is going to VP to VP NP. Verb can be include. NP can go to proper noun or determiner nominal. So we can go determiner nominal. Okay, and determiner can be there's that. So we can get a, and nominal can be a noun. Nominal noun or a nominal PP, and so noun can be book, flight, meal. So no.
What's nominal?
It's a partial NP without a determiner. Okay, it's a.
It's not in the lexicon.
It's a non-terminal. So nominals get expanded to nouns, nominal nouns, and nominal PPs. Okay, but you wanted a Houston. Okay, and Houston's a proper noun, okay, and proper nouns go to NPs, and they can't have a determiner before them, okay, so actually you can't have a Houston, okay, thank you, it wasn't the example quite I wanted, but, so it has got some restrictions on it.
I book a flight to Houston.
Thank you. That's like a perfectly reasonable sentence, which I hope, actually, is in the grammar. I book a flight to Houston. Is that what you said? So we have NP gets expanded to a pronoun. Pronoun gets expanded to I. we're going to have the verb phrase. The verb phrase gets expanded to we have a flight to Houston, so we can have the verb going to book, and then NP being we can do determiner to nominal and get the PP, so we can get the to Houston. Okay, but there's actually two ways to do it. We could make it verb goes to a flight to Houston, or we could make this rule where we could make this a flight and this is to Houston. So there's actually two ways to do it, and they mean something different. I don't know what they mean. So, okay, let me try and explain this. Do you understand that there are two ways to parse this? One is that you're booking a flight, and the flight that you're talking about is the flight to Houston. Okay? That's the flight. You're identifying that flight. That flight might be stopping off at Atlanta on the way, so you're not going to Houston, but the flight is going to Houston, and you're booking that particular aeroplane independent of where it's going, but ultimately it's the one that ends up in Houston. Okay? That's one interpretation. Be careful, I'm going to ask you which one you meant. While the other one is, I'd like a flight, any flight, I don't care which one it is, as long as it goes to Houston. Okay? And so the to Houston is about the booking, not about the flight. It's a subtle difference. I'm trying to think if I can give you syntactically the same thing that would make it very clear which one is different. So if we go back to our favourite example of a boy saw the girl with a telescope, okay, the distinction here is that the first one where it's related to, when I said it's the flight to Houston but you're only going to Atlanta on it, that's where the girl is holding the telescope, okay? It's the telescope girl that you actually see, okay? Because it's about the girl, it's not about the seeing. While the other one is the boy saw the girl with the telescope, it's the seeing that happened with the telescope. So the boy's looking through the telescope and seeing the girl, but the girl doesn't have a telescope. So there's a different meaning between the two. So which one did you mean?
Oh, the first one.
That's a good answer. Doesn't matter. But yes, okay, now, here's another question, okay? Can somebody give me a sentence that uses these words, the lexicon, okay, that this grammar does not accept? That's a perfectly reasonable English sentence, okay? Because Houston, 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 Houston is a sentence that can't be accepted by this grammar, but that's not what I want a perfectly reasonable English sentence which cannot be accepted by this grammar.
She does book me a flight.
She does book me a flight. Yes, I think you're actually right about here.
Because it can only start with that.
That's right. So it can only be an actual question, while she's doing this emphatic thing. It's actually not covered, but all of the words are in there. Yes. Okay. So that doesn't work. Okay. Even though that's a perfectly reasonable sentence. Okay. Do you have a different one?
Yeah. I think this grammar doesn't allow sentences to start with a preposition.
That's almost certainly true.
Because the preposition comes from the PP.
And the PP is always going to be followed by some sort of nominal. Yes.
And the PP comes from either the nominal or the verb for phrase.
But can you construct me a sentence
Like
that...
from Houston, I book.
Right.
I don't know if actually that's valid or not.
I don't know if that's valid in English or not. hands up if you think from Houston I book is a perfectly reasonable English sentence that's not said in a Shakespearean play. You think it's reasonable. Okay, you're Singaporean, is that right? You're native. Yeah, so he is native English. As long as we book it through Singapore, then it's perfectly reasonable.
If you replace book with another verb, it would be more reasonable.
I agree. It's a little weird, but you're very likely to actually see it. So again, what you've got this grammar that's made a decision about what's acceptable and what's not, and there's going to be some things that are fully acceptable, and if you were building a flight booking system, you'd probably want to accept that, because people would get annoyed if that didn't work. Okay? And so you do want to be able to expand these things. So be aware that this isn't correct for English. Okay, so it's limiting things. Okay, so the other question I usually ask at this time is, can you give me a sentence which is not English grammatical but is accepted by this? But you guys did this at the beginning. What was the one? Me book, which I think is just excellent. Yes, it's like, well, I know what it means, but it's really weird, and no, but it's completely acceptable by this. Okay, so the grammar is this abstract thing. It's neither true or false in the real world, but it does define a language. And that language that it defines is the thing that we're going to do a parser for. So it's not going to make a decision when it comes back, when you give it a sentence, of going, yes, that's completely acceptable, but that's a stupid thing for anybody to say, so I'm not going to parse it. And likewise, it's not going to say, I can't parse it, but I feel I should because I understand what it means. It's not going to do that. It's going to give a yes or no.
Well, can't you assign a probability to the parsers and say, this is technically valid, it's really rare for someone to say it?
So yes, ultimately you will want to be able to do that, but realistically, you're going to have data to be able to work out what that is. Okay, so you're going to have to be able to train from data, and you're going to have to be able to still parse it and find out how often that actually happens with respect to a big corpus of data. So you're going to need a lot of data to be able to do that. But yes, that's what ultimately you'll be doing, and there is a lecture on that. I think the week after next, on building probabilistic context-free grammars and how you learn them from data and what corpora you're using to be able to train from. Although it's often quite hard to find the corpora to do the examples to be able to do that, because what you find is that people do non-obvious things all the time, but there's an awful lot of non-obvious things. So you need an awful lot of data to be able to get these estimates correct. So we talked about top-down and bottom-up. We can have a simple thing that basically we start at the top, we start with the S thing at the top, and what we're trying to do is we're trying to expand that S and keep expanding that S until we find our actual sentence. I'm going to run through an example on the board. And alternatively, what we can do is we can do bottom up, where what we do is we basically start at the bottom with all the words, and then what we do is we try to join them together in order to be able to get the thing that we're actually looking for. So I'm going to make it an even simpler grammar, okay? And I'm not going to ask you what sentence. I'm going to define what it is because I want the thing to work, although it's pretty limited in what it actually is. But, I think there's 4 sentences it can do. So if we're doing top down, okay, and what we're trying to get is the sentence John flies Delta, okay, that's the sentence we're trying to get. It is really simple, okay, that we're going to have an S to start off with, and what we're going to do is we're going to expand that S into anything that we can expand it to be in, and there is only one rule in this case, which is S goes to NPVP. So what we can do is say the next line is NPVP. Okay, we have a choice. We could expand this one or this one, but let's do left side first. So we can expand the NP, okay, to John VP, or we can expand it to be Delta, okay. but that one turns out to be not right. So it's a sort of bogus one that we actually did, and it's not right. But we would get that and have to search for that. Okay. Our next task would be expanding the VP, and so if we take the John one, we then expand the VP to, what did it say, VNP, and then we can expand the John to flies NP, and then we can expand the John flies. Well, again, there's two, so there's John and John flies delta, which was the one that we were actually looking at. Now, this one and this one are not part of what's called the derivation, okay? Because they don't lead to the answer, because I said that I was looking for John flies delta, okay? But they are sort of valid at what you would look the way. Now, I mentioned earlier about parsing and saying that we would get a derivation, okay? A derivation, okay, is basically showing your work. And basically a derivation for this sentence would be S, NP, VP, John, VP, this one, and this one, because it shows you what you actually expanded. But there's other ways to show exactly the same information, and often this gets shown as a parse tree, okay, because some people can read these things better. And this and these have the same information on it. And we're not going to give you the task of, given one of these, can you print out one of these? Now, this of course is a graph, and we all know this is not going to work on your standard ASCII terminal. If you're all old enough to know what a terminal is, I know you all know what a terminal is. And so often we write it as a bracketed structure. So we have an S open brackets NT. Okay, and then we want the NP, and then we'll have John, and then we're going to have the VP, and then we're going to have the V, and then actually we're going to have, no, we're going to do that, we're going to have V, and then we're going to have flies, and then we're going to have the NP. See, I really need a chalkboard that does bracket matching. Okay, close all the brackets. So you get a string like this, okay? And of course, this has got a nice form that you can read back and print out and do other processing on, okay? It's actually called an S expression, but nobody really calls it that anymore. So here we have an expansion. This is top down because we went from here to here. Okay, this is a derivation. There are some of these things that if you naively do it and search everywhere, you get these things. Theoretically, you could continue to expand that one, okay, but you can maybe have something to check that because we have a delta here and we have a John here, it's never going to match, okay. And so we have top down. We have a tree structure which has the same information in it. This is also called a derivation, okay. And then we have some bracketed structure form that gives you the same information. Notice there's sort of a choice on how we exactly represent where the brackets go in here, and there is a choice, okay? But there's some standard that would work that would allow you to be able to take one of these, generate one of these, or generate one of these, or be able to generate from any one, generate the other one in a fairly fixed algorithmic way that is not ambiguous, okay? Now, it's possible for some parses that there are multiple derivations for the same sentence. We had the example about something. The flight to Houston was ambiguous, and therefore I had two different parses. It has two different derivations, and therefore there's different ways to expand it. There's a different tree, and there's a different bracketed structure. And so if you want to parse it, you want both, probably, or you at least want to admit that you only found one. Okay, because there could be more than one, and it's very, very common in natural language that there's multiple. One of the things that's actually pretty common about human natural language is that it has a lot of ambiguity in it, and the listener is really good at not even noticing the ambiguity. Okay, we are just so good at that. We only take the most reasonable interpretation. I mean, occasionally, and it's funny when we don't get the right interpretation and we misinterpret things. Okay, but in general, we're pretty good at it. But machines are pretty stupid at it, and they end up finding the wrong interpretation of things, and therefore end up doing the wrong thing. Okay. So I showed the top-down one. What I wanted to also do was show the bottom-up one. Okay, even though it seems obvious, but this is the sort of thing that people would put in exams and ask you questions. So I know that you're here just to learn how to do the exams rather than to learn about natural language processing. So if we have John flies delta, okay, so I'm going to call this bottom up, even though I'm starting from the top of the board, but I think you're bright enough to deal with that. And what we're doing is we're starting from the words and we're actually converting them. So the first thing you can do is John, and because we have a rule that goes to NP, we can replace that with NP flies delta. We can then do flies, can be a verb, delta, and we have an NP, NP, and then we have an NP VP using the VP to V NP rule, and then we can have an S. Okay, and that's going this way is top down, and well, going this way, but from words to final token is bottom up. Okay, so this is the sort of thing that we might ask you, or you should just be aware of, that when you're looking for derivations, you want to know what the actual rules were used to do the expansions. You want to be aware that a set of written forms like this, or the tree that I deleted, or the bracketed expression, are all examples of derivations, and some of them are easier to read than others, and some of them easier to produce if you actually have a program. This is probably the easiest one to produce. The tree, well, you have to have some graphing software, and this one is dead easy to do, and if you write a program to do it, I can guarantee you'll get the number of brackets right at the end if the program's doing it, but if you have to write it out, you'll probably get the brackets wrong.
Like the long approach, what happens if like one word has multiple labels? Like flies, for example, could be like a noun phrase.
Right, okay, so what you can do is that would be multiple derivations if, okay, they all lead to a complete parse at the end. If they're just ambiguous, as here, then they're not going to lead to a derivation, okay? And they're just going to be a potential dead end that you're actually doing. And if you're asked for a derivation, you wouldn't show the ones that don't work, but when you're writing a program to do it, it's going to have to search that space, okay? So yes, there could easily be, and in fact there almost always are ambiguous things that you don't know, and they're short-term ambiguous and they don't lead to a parse, but your parser basically has to go and search that space. Yeah. So far we've talked about these grammar rules, okay, and a number of algorithms that deal with context-free grammars sometimes put restrictions on the shape of the rules that can appear in the grammar form. And the most common one, in fact it's incredibly common, is called Chomsky normal form, also called Greibach normal form, where basically the rules are limited to the number of tokens that can appear on the right-hand side. So instead of allowing 0 or more, it allows 2 and only 2. Actually, sometimes it's a terminal or 2 and only 2, depending on the exact definition of it. But basically, you're limited to basically binary branching rules, okay? And it makes a lot of algorithms a lot easier. I think I'm going to naively say, until somebody shows me that I'm wrong, that all of the automatic training methods for finding grammar rules always find binary rules rather than 0 or more. If you get a linguist to write them, they will rarely write a rule with more than 3 or maybe 4 daughters. So there's not an arbitrary number. but putting them into Chomsky normal form is an extremely common thing to do. And in fact, most of our grammars will have two and only two daughters, so binary branching rules is the standard form for doing it. Now, that's not a problem in an abstract sense, but if you're really looking for the parse and you want it to be a linguistic parse, it is an issue because it's not the same shape of what you actually want. Even though it might be isomorphic to something, there might be a conversion routine that does it. And in fact, there is a proof that shows that all, let's see if I get this right, all languages that are context-free can be described in a Chomsky normal form grammar. Okay? You do not need to have 0 or more things at the right-hand side. You can always rewrite them to be binary branching, and it's very simple when you think about it. If you have 3 things on the right-hand side, what you simply do is you introduce a new non-terminal that you haven't used before, and you call that x2, and then you just say x goes to ax2 and x2 goes to bc, and it's going to accept the same grammar. It's not going to give you the same parse because there's now going to be an extra level in it. There's going to be an extra part of the derivation. So it's still going to accept the same language, but you get a different shape of tree out of it. And some people really care about that, and some people really don't care about that. If you care about it, you've got to be able to find ways, and there are ways to put it back again post hoc. Okay, but you can actually convert everything to that form. Okay. So here's our earlier grammar converted. No, it isn't. Here's our earlier grammar, and it is converted. So we have s goes to x2 pp, where x2 gets expanded somewhere, and here verb to. So we make sure that everything either has a single non-terminal or 2 and only 2. Okay, and so we can do that. You should be aware of it. If you want to impress somebody when they ask you about, they tell you about their grammar, ask if it's in Chomsky normal form. Okay, they'll be pleased that you're interested. Even if you're not interested, just ask them for that. Okay, and they'll treat you better and give you another cup of coffee. Now, we're going to look at this new algorithm called the CKY or the CYK algorithm. It's arbitrarily, it's one of these quantum decision things, it's both. And as soon as you name it, it sticks to that while you're on the page. If I go back to the previous page and come back to this, it will say CYK. This algorithm allows you to parse arbitrary context-free grammars. Okay, but actually only Chomsky normal form grammars. So it requires the rules to be binary branching. Okay, we've shown that we can take any arbitrary context-free grammar and convert it into one of those, but it must be converted before this algorithm is going to work. Okay, you can think about this algorithm in terms of a big matrix where the diagonal is the words that you're actually trying to parse, and the columns are effectively the points between the words. In fact, let's actually just look at it like this. So we end up with book this flight through Houston. Okay, so we're only going to use the upper half of it. We have book this flight through Houston. Okay, and basically the columns are markers where we are for the words in the sentence. And what we're going to do is we're actually going to build the derivations up on the right-hand side, and there may be lists of things that are going to be there. Okay. So the first thing we actually do is we insert the words. So this is what is actually inserting the words. So this is actually putting in within the just one down from the diagonal, putting in the some word goes to some particular word, and you put that in. And then what we do is we go through every single thing in every node. Every box in the matrix and try to fill things in, but we have to fill them in a particular order in order to be able to build on top of them. And basically the order that we have to fill them in is basically these diagonals, okay, as we go on. It doesn't actually have to be these diagonals, but the point is that you can't fill anything in until the bottom things have been filled in. Okay, so we can't fill in this square unless this square and this square is filled in. We can't fill in this square unless this square and this square, this square and this square is filled in. And of course this one can't be filled in unless this one and this one is filled in. So any ones which are to the below or left have to be filled in before you can fill them in. Okay, that's actually a perfectly reasonable constraint. It's not really as graphical as what it is. It means I depend on the things that are joining the words below me in order to be able to continue. So it's a bit like the bottom up, where basically you couldn't have put the VP in here because you don't know about the flies and the delta being changed into a verb and into a noun phrase. So the first thing we can do with the rules is basically we can fill in noun for book because we know about book and we know that it goes from each of those, and we can fill in any other things that are at the it's also a verb because we can just have Jason's simplest possible sentence, book. Okay, so and it is a verb in this case, so that's the one that's going to win in the end. We then can put in the rest of the non-terminals, determiner, noun, prep, and proper noun. Okay, for each of those, and we also can put in NP here, so it's not just a proper noun because a proper noun then leads to an NP at this point, so it's not just that first one, we can build on top of it. Then we can put an NP here because we've got a determiner and a noun, so we can join these things together. We can do something else in this one. Well, there's nothing on the top right and the top because nothing joins. The noun to determiner and the verb to determiner has no possible thing, so I'm putting a little line in there. We've visited it, but we haven't actually, can't put anything in there. And likewise for this one, the noun and the prep can't join together because there's no rule that allows us to join these together. Likewise, we can't do anything here because we have to have the NP and the prep to join together because there's nothing that allows us to join these together. But we can join the prep and the NP together to be able to get a PP. So we've now got a prepositional phrase here. And we can't join the prepositional phrase to the noun, but we can join the prepositional phrase to the NP to form another NP up here, which is this flight through Houston. And then we can join the lastly, when I then go along the top. So we can get a VP out of the verb for book. We can get the next one. We can also get a sentence there where we get the sentence book, but it hasn't used everything. So although it is a valid parse, it's ignoring all the rest of the words. And you have to be careful about this. I would say that 80% of all parsers I have ever written have not had that condition properly in the first time we've done it, and it always finds initial substrings which are sentences and goes, yeah, I found a sentence, and the answer is yes, but you've ignored half the words. Okay, and so you then go and fix it. And so although that is a sentence for book, it doesn't deal with all the words. And even book this flight is not doesn't deal with all the words. Okay. Then we get nothing, and then we get our final S right at the top. So we get the S that we're looking for, and it deals with all the words, and so that's the correct parse. There may be multiple ones. Okay. It could be that the PP attaches to the verb phrase rather than the noun, and then it would have this weird meaning of the act of booking gets done while you're traveling. And therefore, in order to book this flight, you have to do the booking while you're through Houston or going through Houston. Okay, so it could mean that, but it doesn't. And the grammar doesn't allow it, so you don't actually have the example of So we go back to the algorithm again. So basically, again, what we're doing is we're filling in that diagonal, and then we're going through each of the boxes, and we're looking at the things to the left and the right, and we are finding out if there's any rule that allows us to be able to join these things together with things like that. If they are, we insert the found non-terminal, and we keep doing this until we get to the end. And it's true if we actually have a sentence which is in the constituent in the top right-hand box, it goes from 0 to the end of the sentence. We can also look at this as a logical form, so we can come up with a bunch of logical expressions which mean exactly the same thing. If you're happier with writing algorithms like this, you can, and sometimes this is a good way to do it. There is a programming language called Prolog that hopefully none of you are old enough to remember. Has anybody heard of Prolog? It's a logical programming language that allows you to write in declarative style rather than an applicative style, and you can write rules effectively directly like that, and it would work, okay, and it would do the right thing. There's a couple of things I haven't talked about in this algorithm that you have to be a little careful about-ish, depending how you implement. There could be infinite loops that disappear into nothingness. If you have any rules that are left recursive, so if you had anything that went like S goes to S and S, which is a perfectly reasonable rule to have, so that is, you can have sentences like John loves Mary and Mary loves John, perfectly reasonable rule, but you could actually end up applying this rule an infinite number of times because you're going, yeah, do I have anything to expand S? Yes, I have this rule. Do I have anything to expand S? Yes, I have this rule. And you could keep hypothesizing that rule, so you have to be careful in some way not to do that. And so you have to be a little careful about that because it can actually break things if you're not careful. The CKY algorithm complexity is, worst case, is number of words cubed times the number of rows in the grammar. Okay, that's not very good because most parsers can be a little better than that. Although one of the things that's sort of interesting is the best case for CKY is also the worst case. You've always got to do that, so it's not less. For some grammars, it's always the case that it's basically n cubed, okay? Because this is sort of a constant. And so that's not ideal. And so it's computationally quite expensive. And you might think, yeah, but, you know, sentences aren't very long. Yeah, but n cubed is really bad when you've got 20 words in your sentence, okay? And it does take a long time, okay? Especially if you've got, you know, a Google amount of data to actually parse, it can be actually a problem.
So what is the advantage this algorithm has over just doing a tree search? Like you had some top-bottom search, and you could leave a prune right there where, like, you know, the first word was delta, so you can get rid of that.
So what I did on the board was effectively CKY with one look ahead. Okay, with actually looking to see whether the next thing, which is called, it's got a name, hang on, it'll come to me, LL1 is the term that they used to, so you're looking ahead one. And so it's effectively the same thing and computationally the same thing. The thing that you can get other algorithms advantages for is there's less sub-searching when you don't know what you're looking for. It happened to be that any time that there was an ambiguity, I only actually had to look at the next word. That's not always the case, okay? And that makes it a little bit harder. Almost everything in the worst case ends up with n cubed. Almost all algorithms are n cubed in the worst case because what it is any possible bracketing. And if you have a string of n things, the number of possible bracketing in it is n cubed. I'll let you think about that.
From the table, you are just filling half of the table, and the table is n squared. So half the table is O n squared.
Yes, but there might be multiple things in each box. Okay, so it's n squared. It's actually technically n squared divided by 2, but we usually don't care about that. But there may be multiple things in each box, and theoretically there could be, for every single rule, there could be something in that box.
And that's where the G comes in.
The G comes in, you've got to look them up. The cube part, as opposed to the square part, comes in that what you're going to do is for every single grammar rule, you could have a new entry there, which is going to multiply the next level up. You probably don't, because it would be weird to have something as complex as that. Okay, but that's where the cube comes from. Okay, so it's all possible combinations, but all times all possible grammar rules, which gets expanded, but you still have to search all possible, so you could maybe say it's G squared times n squared. Okay. So what I've talked about today is context-free grammar parsing. I talked about one particular, I talked about the two things, parsing and recognition. They're different. Okay. There's a really cool algorithm that takes a context-free grammar and converts it into finite state machine, and it allows you to very, very rapidly, like in the length of the sentence, to tell you whether it's in the grammar or not. Okay, it was done by a young Scottish researcher 30 years ago by the name of Alan Black. That's why I happened to mention that one. And a number of people have used it. It makes some assumptions about the depth that you do, but it limits on the depth of the sentence, so it's sort of correct, although theoretically it's not, but practically it is. And so you can do recognition of what effectively are context-free grammars if they're finite length sentences, which all human sentences are finite length, at least up until now, unless that person is still speaking and going to continue to speak forever, but we're going to ignore them. But parsing and recognition are two different problems, okay? And usually recognition is a little bit more efficient, and for some tasks we're only interested in recognition. So in speech recognition we're often interested in, is this a valid sentence? But I don't really care what the parse is, okay? Because I want to get rid of all the ones that are not valid, okay? Because I'm not going to continue to search in the speech recognizer, or if I'm doing machine translation, I want to translate something that's a valid sentence within the grammar. So I maybe want to do that, and I don't care about the ones that are outside it. So I want a recognition thing, and I want to be really efficient because I'm going to do it billions of times while I'm running my algorithm. Parsing, however, okay, is telling you what you actually did to do it and recording the information to be able to do it. Not just looking for one parse, but usually looking for all of the parses that are in there. And to do that, you have to show the derivation. So you want to show all of these either expansions, the tree, or the bracketed expression. Almost all of these algorithms can be done bottom up or top down. There are some advantages in doing one over the other, depending on the context that you're actually doing. Remember, one of the things that we've talked about in this course so far is you have lots of options in NLP, and make sure you choose the best one for your particular application that you're dealing with, because it might not be that there's one size fits all, and there might be something that is actually better or easier for you, and therefore a top-down might be better. It might be more efficient for what you're actually doing. Bottom-up might be better, especially if you were trying to do some sort of incremental thing. It might be better to be able to do bottom-up. Okay. We talked about the CYK algorithm, and we said it is for Chomsky normal form, but realistically almost everything's for Chomsky normal form is really wants binary branching rules. Okay. Next we're going to talk about a more generalized form of the CKY algorithm, although it was developed completely independently. Something called Early's algorithm. It's often called chart parsing. It's called Early's algorithm after the developer of this, a guy called J. Early, who did his PhD at Carnegie Mellon University so long ago. Well, I was born, but I was pretty small. Actually, before even CMU was into speech and language, so it was something like 1966 that he did it, and it's really quite amazing that such an algorithm came up at that time when nobody was really caring about parsing at the time. So J. Early did this. He's not in the field anymore. I've not met him. But we're going to talk about Early's algorithm next week. Okay, that's it for today. Okay, thank you.